So today what we're going to be doing is we're going to be graphing an absolute value graph, and this is going to be a three-part section because I wanted to break it down into something that makes it a little more intuitive, and we're going to be graphing from a parent graph perspective. Now again, this can be done all at once, and oftentimes this is taught as a single unit. I'm going to break it down into three different pieces so we can intuitively figure out what's going on with a graph when we start with the parent graph and when we start transforming it to look more like this general setup. Now, what is a parent graph? A parent graph is the starting graph, or the absolute simplest form of the graph that we can get without adding, subtracting, multiplying, or dividing. In this case, y is the absolute value of x. I cannot get that any simpler, so we call it the parent. Anything we do to this graph changes the parent, and we would technically call these child graphs, but we're going to just call them the transformed graphs. So the transformation steps here are, if I multiply it, we're going to be stretching it. If I add or subtract inside the brackets, I'm moving it left and right. If I add or subtract outside the brackets, I'm moving it up or down. So the first thought you might have is, okay, what does the parent graph look like? So let's go ahead and let's graph that. This is the parent equation. So we're going to create an XY table with a few values to see what it looks like. Let's start with, let's say, -2. -1, 0, 1, and 2. And I'm going to plug all of those values into my absolute value brackets. The absolute value, we remember the absolute distance from 0 is what we're after. So -2 is still 2 units to the left of 0, so the absolute value of -2 is 2. Likewise, the absolute value of -1 is 1, 0. In this case, even though -1 was 1 unit away from 0, so we got a +1, +1 is also 1 unit away from 0, so it is +1. And we notice we always end up with a positive value on the end. Let's graph these points and see what we get. Where did we get those points? Well, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. We took each one of these and plugged it into the equation right here. And then we got the result by performing order of operations on what we applied. And we notice that our graph has a nice V shape, y equals the absolute value of x. So that's where the V shape looks. It opens upward. So let's start playing around with it. On this first one, what we're going to be doing is I'm going to graph my parent graph so I can see what I've done to the graph by performing these series of transformations. So this is my y equals the absolute value of x. And just so I can see the change, I'm going to do my transformed graph, or my child graph, in red. And to see what I've actually done, I'm going to use the same set of points. So I can say, okay, if these were the points up here, these are my new points, I can see where it's been maneuvered to. If I plug in a -2, -1, 0, 1, and 2, all into my equation, I'll see what I get. And so one common mistake that a lot of students make is they'll say, hey, I can't have a negative. And what they'll try and do is they'll try and say, okay, I can't have a negative, so let's make that 2 + 1. That's not what we want to do. The absolute value, if we consider them a set of parentheses, is to be applied at the end of whatever we do in here. So what we're actually going to do is we're going to take -2 and add 1 and get -1, and then we'll make that a +1. We'll take that and say, okay, that's a 0, then we'll make that a +0, or just 0 in this case. We apply it at the end of what we're doing. And so let's see where this graph at -2, 1 -1, 0, 0, 1, 1, 2, 2, 3, where it falls. And what we notice is that our graph looks like it's been shifted to the left. So we know that our transformation, each piece has been shifted to the left by 1 unit. And so we can make a general rule that says, hey, that must mean that is to the left by 1. So I'm going to come up here and I'm going to write that down. I'm going to say, hey, if I have an x plus h, I know that that must be a left movement. And so what happens if we have not a plus 1, but let's say we have a minus something? What would that do to our graph? Well, let's see. I'm going to take each of these points, and I'm going to plug it in to my equation up here. I'm going to plug a -2 in for x, a -1 in for x, a 0, a 1, and a 2. I'm plugging them all in for x. What I do after that is I'm going to subtract 2 from each one of them, and then I'm going to make whatever value they create positive. So I'm going to see what it does to this graph. And there's my y equals the absolute value of x. So what we get is I get a -4, because I take -2 minus 2, which is -4. And then I make that a +4. Get a -3, get a -2, -1, and a 0. Which means that my new graph, -2, is way up here at 4, 3, 2, 1, 0. And what I see right now is I see a straight line. If I were to connect all those points, I don't know where my V is. I don't have a bend. But if we take what we already know, and I think about if that was moved left 1 by adding, we can kind of assume that this is the opposite. The opposite of left must be right. I bet you that was moved to the right too, which means that vertex has moved to the right 2 units, which means I might need to plug in a 3. I plug in a 3. Yes, in fact, I do get the bounce. So there's my y equals the absolute value of x minus 2. Oh, that's a vertical line. Ignore the fact that I tried to bend it there. And so we notice that each one of these original points has been moved to the right by 2 units. The entire blue graph has shifted to the right, to the red graph. So, now, those are both what happens inside the parentheses. In fact, x minus h is right. So I know inside what happens left and right, but what happens when it's outside? How do we look at that? If I have an x close absolute value bracket, minus 4. Well, I've already given you a hint. I've told you it's an up-down motion, which means that's either going to be up 4 or down 4. And so let's see which one we get. So if I have my x and my y table, -2, -1, 0, 1, and 2, plug it in, we'll see which one we get. And so in this case, I'm going to take -2, then I'm going to make that positive before I subtract, because that's where the absolute value brackets end. I'm not going to take -2 and subtract 4 and then do it, because that's not what it's telling me to do. it says, hey, make this a positive number, 2, then subtract 4 for negative 2. It's going to say, hey, make this negative 1 positive 1, then subtract 4 for negative 3. Make it positive, then subtract 4. Make it positive, which it already is, then subtract 4. Make this a positive, which it already is, and then subtract 4. So we know our new graph is down here, which looks like that movement y equals absolute value of x minus 4. Looks like that movement took the entire graph and moved it downward. Each of these points has been moved down by 4 units. So the entire graph has moved down. So we can chalk that up to another rule. Down by 4. Which means we can again come over to our set of rules and say, hey, if I have the absolute value of x minus k on the outside, that is down. And by conclusion, we can say plus k means up. So let's knock out this last one. But with this last one, we're going to save some time because I think at this point, we know how the graph works, so we don't need to draw the table. If you get confused, or you forget the rules, or you don't remember what's up, what's down, or what's left, or what's right, we can always make a table. But I think at this point, we can safely look at the parent graph, which we know it creates a perfect diagonal and a perfect diagonal of y equals the absolute value of x. And we can say, hey, I know that this graph was moved left 1, which means I'm going to take this vertex and move it to the left 1, and then I'm going to move it up 2. So left 1, up 2. And up here, I'm going to draw my perfect diagonal to the right. I'm going to draw my perfect diagonal to the left. And there's my y equals the absolute value of x plus 1 plus 2. There we go. That's how you graph from a parent graph. Okay, so today we're going to be graphing absolute value again, except for this time we're going to be doing something called a dilation. Now, this is where we either stretch it towards infinity or we stretch it towards 0, which is going to be called a compression. And now, this is one of the topics that we're going to get into is we're not really sure whether or not we're stretching the graph or if we're just stretching our perspective. That's going to be, we're going to be unable to tell the difference from this point and in many future lessons. So we're not necessarily going to worry about where this change is coming from. Is it coming from us or is it coming from the math? So let's take a look at our first dilation. Our first dilation is a very simple dilation. We have a negative sign out front. And if we remember, yesterday we said our parent graph always had a perfect diagonal right through the origin. And there's my y equals the absolute value of x. What we're going to do is we're going to see what happens when we have a dilation of a negative number. Well, let's go ahead and let's make a table of values for some numbers that we used yesterday. -2, -1, 0, 1, and 2. So I'm going to plug all of these in to my equation. Now, here's the thing. My equation says I have to take the absolute value and I have to make it negative, which many of us look at and we're like, can we do that? Can I plug in a -2 and get something other than a positive number? Well, let's take a look at the order of the steps. So after my first iteration, when I plug in the absolute value brackets, that negative didn't go anywhere. But my -2 did become a +2. And same thing with each one. My negative didn't do anything, but my -1 is now a +1. My 0 is still a 0. My +1 remains a +1, and my +2 remains a +2.
which means that we actually just have negative values. Boom. And so if we graph these points at -2, -2, -1, 0, we see that our graph has completely flipped upside down. And boom, there's our first dilation. We've taken the graph and we're now looking at upside down. Now, did that come from the graph being manipulated? Did we compress it through the origin? Did we change our perspective? Are we now looking at it upside down? That's going to be difficult to prove. So let's just understand that that is a dilation. Some perspective has been changed, and let's move forward. Another common dilation is going to be if we have a 2, which is going to be what we call a stretch. So let's take a look. Let's pop this, our parent graph, onto the grid. Y equals the absolute value of x. Let's see what happens if I have a 2 out front by making an XY chart and using those common values that we've been using. Now we're going to pop each one of those in to our absolute value brackets. I'm going to plug in a -2, -1, 0, 1, and a 2. After my first iteration, anything inside the absolute value brackets becomes positive. And then I double it, which gets me 4, 2, 0, 2, and 4. So what I notice is that my graph, each one of my points has doubled the y value. What was a 2 right here is now a 4 right here. We literally doubled the height of each point. And so it looks like I'm going up 2 over 1 from each one of these. Y equals 2 absolute value of x. And so what was a perfect diagonal of going up 1 over 1 every single time is now a slightly stretched diagonal of going up 2 over 1 each time. So let's see, let's do one more. See if we can't spot a pattern going on here. So I'm going to graph my parent graph that is a perfect diagonal of y equals the absolute value of x. And I'm going to say, okay, what's going to happen with the 1/3? Well, if that made it taller and skinnier, I bet you this is going to make it the opposite. I bet you it's going to make it shorter and fatter. Well, let's try it out. -2, -1, 0, 1, and 2. That's what we have right here. So we have our 1/3 of a -2, -1, 0, 1, and 2. And after my first iteration, everything inside the brackets becomes positive. And after my second iteration, I get a 2/3, 1/3, 0, 1/3, and 2/3. And so I notice that each one of these looks like it's gone down a significant amount, which in this case, I bet you if I continue that further, 0, 1/3, 2/3, I bet you that would be 3/3. And if I plugged it in, 1/3 of 3 is 1/3 of 3, which is 1. There's my next point. And so what we notice is that there's a pattern going on with this diagonal. I was going up 1 over 1 with the parent graph each time. Now this time, between my origin and my next whole point right here, I went up 1 over 3. So where do I see an up 1 over 3 on my equation? the number out front. So I bet you if we use that, we won't need to build a table. We can just find the vertex and follow that slope. So let's give it a shot. Let's see if I can do that to this problem. Well, if my perfect diagonal on my parent function was 1 over 1, and I reflect it across the y-axis, I bet you this one is going to be down 5 over 7. Well, I can't fit that on there, so what I'm going to do is I'm going to say my graph is by 2's, which shouldn't change my parent function, because instead of going up 1 over 1, I'm going up 2 over 2, which is the same thing. So if I do these by 2's, I'm going to put a point in the middle. I'm going to go down 5, 2, 4, 5, and I'm going to go over 7, 2, 4, 6, 7. And I'm going to mirror that. Instead of going over 7 to the right, I'm going to go over to 7 to the left. In fact, this works. We can just simply look at this number right here and see what the rise and the run are. Here we have a rise of -5 and we have a run of 7. If you wanted to test those points, you could. If I wanted to say, can I plug in and get this number? Well, let's see. If I plug in a -7 into my -5/7, -7, that's -5/7 of +7, which cancels out. That is a -5, which is indeed that point right there. If I plugged in a 0, -5/7 of the absolute value of 0, which means -5/7 of 0, which is 0. That point's included. And even if we include a +7, remember, because of the nature of the absolute value brackets, it doesn't matter where we started, it ends up being a positive, which cancels out, and I get a -5, which is in fact that point. So yes, this method does work. And even if we have other translations in the equation, I know that I can read these as okay, that's a left 2 and up 2. So left 2, up 2, that's where I'm going to put my vertex. This -2 over 1 tells me I have a rise of -2 and a run of 1. So rise -2 and run 1, and then reflect that in the other direction. So when I go to the right, when I run to the left. And I notice that this works extremely well. So we get this graph. In fact, any graph, as long as we move it and then stretch it, we're good. So even with this one down here, I'm going to be moving it to the right by 4 and down 1, and I'm going to have a rise of 1 and a run of 5 in both directions. So right 4, down 1, there's my vertex. If I rise 1, run over 5, well, that's way over here. If I rise 1, go over 5 in the other direction, I get that right there. So, kind of missed my point there, but let's assume that went through there. So anytime we have an absolute value function, we know the slope and we know the starting point. And that's all we need to graph any absolute value function. So now that we know how to graph absolute value graphs, we're going to graph something a little more fun. These are called piecewise graphs. In piecewise graphs, for lack of a better phrase, they're like Frankenstein graphs. We take a little piece of this and a little piece of that, and we just smash them together, and we create this new Frankenstein monster, of which we're going to call, from this point forward, piecewise. Because Frankenstein was a wise and peaceful monster, right? Yeah, we all know that. So let's move forward. So even though the graph should go on forever towards infinity, we're going to keep it within the bounds stated. We know the fact that, let's say, like with Frankenstein, that arm came from a whole human being, but we don't care about the rest of the human being. We just care about the arm, and we stick it on our monster.
So this is going to tell us what parts of what monster we want. Now, there's going to be a border here. And what I've done in this section is I've listed exactly where the border is. Next section, we're going to be going over how it's actually going to look instead of listed like this. So what you can do is you can say, hey, I have a left of 0 and a right of 0 graph. So I'm going to be doing my left of 0 graph in red, and I'm going to be doing my right of 0 graph in blue, and I'm going to go ahead and draw a border in purple. So my 0 is going to be a vertical line right here where I separate my graphs. It's going to be on left side and on right side. So let's take a look. The left of 0 is x plus 2. I know that this is a right to absolute value equation. So I'm going to say 1, 2. And because the number out here doesn't exist, I know this is going to go up 1 over 1, up 1 over 1, all the way. Even though I know it keeps going forever, I stop at the boundary. So it's just going to be that piece. And it's going to mirror, so it's going to go up 1 over 1, up 1 over 1, up 1 over 1. It's going to continue on forever over in this direction because guess what? There's no boundary. So here's my y equals the absolute value of x plus 2. My right of 0 is x minus 2, which tells me, oh, I straight up described that wrong up here. That is a left by 2 movement, because my minus 2 is going to be my right 2 movement. So I'm going to take my vertex and move it 2 spots to the right. And I'm going to go up 1 over 1, up 1 over 1, up 1 over 1, and I'm going to graph going on towards infinity, and I'm going to mirror that off to the left, up 1 over 1. Ooh, but I can't go on past the boundary, so this is my y equals the absolute value of x minus 2. And it's as easy as that. So we're going to take each graph, and I'm going to graph the part of the graph to the left and the part of the graph to the right. And that boundary can be anywhere. As we see with the next one, this boundary is at positive 2. So at positive 2, I'm going to draw myself a nice fat boundary. And I'm going to say, okay, cool. My left of positive 2, I'm going to draw in red. And this hasn't moved, and it hasn't been scaled, so I know it's the parent graph, which is that, ooh, almost perfect diagonal, but it stopped at the boundary. And then a perfect diagonal off over in this direction. So I'm not going to draw an arrow here, because guess what? This continues. Does my right side continue? No, it doesn't. So here's my y equals the absolute value of x. It goes off to the right and stops, and it goes off to the left and doesn't stop because it goes on forever towards infinity. I'm going to draw my right side in blue. And now this minus 5 means it's been moved 1, 2, 3, 4, 5. There's no coefficient right here, so I know it's actually going to go up 1 over 1 and up 1 over 1 all the way until it hits the boundary. Now, depending on how you scaled it, you might actually have some values off to the right, which is why I drew an up arrow, because it is going up. Does it go beyond this boundary? No, it stops. So I'm not going to draw an arrow this way. There's my graph. So it's not too bad. Most of these are just going to be as simple as left of the number and right of the number and knowing where our transformations are going to put that vertex. So left of 1, 2, 3, negative 3. I'm going to draw my boundary at negative 3. I know my left one, I'm going to draw this in red. And now in this case, not only has it moved, in this case, to the left 1, 2, 3, 4, this has also been moved up by 1. So my vertex is up here. And I draw my line going to the right, and it stops. I draw my line to the left, and it doesn't stop. So it continues on forever in that direction, but it stops right there. My graph to the right, okay,
this has been moved to the right by 1 and up 1. So my graph is right there. And I just go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. And then I reflect that movement all the way back here. And so then the question I ask myself is, does it continue going to the right? Yes, it does. So if it continues, I go ahead and I put an arrow. Second question is, I ask, does it continue going to the left? No, it stops right there. So I'm not going to draw an arrow to the left because it doesn't continue. So let's try one more. So again, I have my left of 0 and my right of 0 that I'm doing in red, and then my right side I'm doing in blue. So again, I have my border right along 0. In this case, I have a x plus 1 and an x plus 2, which means that's left 1, up 2. Again, that coefficient is positive, so I'm going to go up, and I hit the boundary. And I'm going to go up when I don't hit a boundary, so guess what? I keep going. There's my y equals absolute value of x plus 1 plus 2. And then over here, I have minus 1, which means it's been shifted to the right one, but in this case, it's moved down by 2. So I'm going to draw my absolute value graph like this. I'm not going to draw an arrow to the left because it stops right there, but I will draw an arrow to the right because it keeps going. And there's my y equals absolute value of x minus 1 minus 2. And then the last two, just to see a little bit of what we could see. This one's at positive 1. And this is the first one that I have, that I notice I have a coefficient, which means this isn't going to open up. This one is going to open down. So I'm going to move left 1, 2. And instead of opening upward, I'm going to have a slope of down 1 over 1, down 1 over 1, down 1 over 1, until I hit that boundary. And does it continue beyond the boundary? No, it doesn't. So I stop, I don't put an arrow. But on this side, does it keep going? Yes. So I draw my arrow. On my right side, you notice how there's no negative coefficient. So on my right side, 1, 2, this one still opens upward like normal. It continues over here. It does not continue to the left, so I don't put an arrow. And so, can I have graphs that are oriented differently? So far, we've only seen graphs that both open upward. Does it matter if they open upward or downward? No. Would it matter if there was a number like 12 in front of it? No. We just graph the graph that's over here, and we graph the other graph that's over there. And we're happy. Okay. Now the last one's a little tricky. So take a moment, pause the video, see if you can't solve this one on your own. Okay. So if you've tried to solve it on your own, you'll notice that these boundaries aren't the same thing. Left of negative 2, which means I'm going to have a boundary right here, and a right of positive 2, which means I'm going to have a boundary over here. Okay, let's see what's going on. So my left of negative 2, I'm going to do in red. That means I've shifted to the left 4 and down 1, so 1, 2, 3, 4, and down 1. I'm going to draw, because there's no coefficient, it must be a slope of 1 over 1. It stops right there. And then I have reflected, and because it doesn't stop, I draw my arrow. Okay, so y equals the absolute value of x plus 4 minus 1. And for my right one, now this is to the right of positive 2, so it's not right here, it's over here. So 1, 2, 3, 4, down 1. I go up 1 over 1, and because it continues, I draw my arrow, and then I go up 1 over 1 in the other direction, and because it doesn't continue, I don't draw my arrow. And that is my y equals absolute value of x minus 4 minus 1. So what happens right here in the middle? Well, according to this, nothing. So there is no graphs. This is empty. Do you need to write empty? No. But this middle area is empty. We could either put a middle graph if we wanted to, or we might say, hey, these graphs only work if it's below a certain value or above a certain value. And when might we see that? Well, we could see, let's say these graphs represent emotions or feelings. Let's say your bank account is really negative. Well, you could have some feelings about that. Let's say your bank account is really big and you have lots of money in there. You could have some feelings about that. Let's say your bank account is just kind of hovering around 0. You may not care. This may be completely normal, so there's no emotion. So is it normal for graphs to have gaps? Could be. In real life, we see it every day. This is what it'll look like in math.